And good morning, everybody. Welcome back to Calc 3. Sorry, going a little bit late due to the truck feed. Plan for today. So I got a quiz for you on standard 14. And then we are going to start talking about integration in standard 15. My next office hours are going to be on Monday from 10 to 10:50 and from 2 to 3. And as far as upcoming homework goes, we do have exam 3 on Monday. And it will be over standards 1 through 14. So, yeah, just like with the last 2 exams, 1 sheet of notes front and back, be similar in format. Once again, I will recommend that you maybe pick like 5 or 6 standards that you want to actually test over and not try to do the whole thing. Better to do really well on a few standards than to only get halfway there on a bunch of standards as far as the mastery system is concerned. Any questions or comments before we get started for today? In that case, an engineer, a physicist, and a mathematician were all asked to hammer a nail into a wall. The engineer built a universal automatic nailer, a device able to hammer every possible nail into every possible wall. The physicist conducted several experiments, and she developed a new technology of hammering nails at super low temperatures. And finally, the mathematician, the mathematician generalized the problem to an n-dimensional problem of penetration of a knotted one-dimensional nail into an n-1-dimensional hyperwall. Several fundamental theorems are proved. No nails ever actually make it into the wall. And with that, I'm going to go ahead and pass out today's quiz. Standard rules apply. Let me know if you have any questions. Luke, you decided you like that seat better now?
I need support for my...
Oh, gotcha. Oh, there's the lefty back there. So mean of them. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. All right. Okay, so in this standard, we are going to change gears. I guess I should make one comment before we start, which is I've graded the quizzes you took on Wednesday, but haven't posted the grades yet. I'm planning on spending the day tomorrow catching up on all my grading for this class, so I'll grade this quiz as well as any retests from the past few days, and I'll post those scores on Blackboard and let you know when they're posted. So by the end of the day tomorrow, you should know exactly where you stand in the class in terms of masteries to help you determine what you need to still test over for Monday. So this standard, we are going to be looking at integration. Specifically, what does it mean to actually integrate a multivariable function? Specifically looking at functions from R2 to R. What does it physically mean? Like, how do we interpret it? And how do we actually do it? What is the calculation process like? So to start off, I thought we'd do just a quick review of Calc 1 integration. So I want to look at what happens when we integrate the function f of x equals x cubed over the interval from -1 to 2. Meaning we have a function, f of x. Let's say here's going to be -1, and here's going to be at x equals 2. And our goal is going to be to determine, first of all, what does the integral tell us about this function? And second of all, how do we actually go about integrating? So first of all, what is the integral of this function actually going to tell us? Meaning, what geometric properties of this graph are we going to find out from evaluating this integral? Avery? Yeah. The integral is going to tell us area under the curve. So specifically, it's going to tell us the area of this piece of the puzzle. But the area between f of x and the x-axis from x equals -1 to x equals 2. Is all of that area going to be considered to be positive area? Jacob?
No, not the stuff left of the y-axis.
Why is that?
Because it's below.
Yeah. And all of this area is going to count as positive area because it's above the x-axis, whereas this area over here is going to count as negative area because it's underneath the x-axis. So we have some positive area, some negative area. It looks to me like the positive area is bigger than the negative area, meaning we should expect, I think, our integral to come out to some positive number. So that's kind of geometrically what the definite integral is telling us. It's giving us this area under the curve. How do we go about actually evaluating this integral? You were asked on like a Calc 1 exam, for instance, to find what would happen if we integrated x cubed from -1 to 2. What would you do? Okay.
Take the antiderivative.
Cool. Let's take an antiderivative. Technically, there's infinitely many. What's your favorite?
X to the fourth over 3.
X to the
C, but then you evaluate that at 2 and also
so 1 over 4x to the 3, you said?
oh, sorry, 1 over 4x to the 4th.
Yeah. We use reverse power rule. We'll add 1 to our exponent, then divide by it. And then technically you could add in any constant you want here, and it should still work because it gets subtracted off. I'm going to choose not to have any constant term, for simplicity's sake. Evaluated from x equals -1 to x equals 2. And if we want to evaluate this from -1 to 2, what are we going to have to end up doing to this expression? You have this 1/4 x to the 4th term. Rob?
You'll have to plug in the 2 for the x, and then the negative, and then the negative. Subtract the negative 1.
Yeah, we're going to plug in x equals 2, plug in x equals -1, and subtract the two expressions. So we'll get 1/4 times 2 to the 4th minus 1/4 times -1 to the 4th, which 2 to the 4th is 2, 4, 8, 16, divided by 4 is 4. -1 to the 4th, that's just positive 1, so this comes out to 4 minus the 4th, which is 16/4 minus a 4th, which is going to be 15/4. So in other words, we do in fact have more positive area under this curve than negative area from -1 to 2. The positive area outweighs the negative area by 15/4. And so the general process in Calc 1 for actually evaluating an integral like this is take an antiderivative of the function. In this case, x cubed becomes 1/4 x to the 4th. Plug in your two endpoints at x equals 2 and x equals -1, and then just subtract them. The theorem, by the way, that tells us we can do this is the good old FTC, the fundamental theorem of calculus. That's the theorem that tells us we can evaluate a definite integral by doing this sort of thing. Any questions or comments about Calc 1 in taking definite integrals? In that case, we're going to move on to looking at Calc 3 integrals now. So the idea of Calc 3 is we're going to have some function from Rn to R. In this packet, we're going to focus on functions from R2 to R. And so the sort of questions we'll be looking at in this sort of questions we're going to be looking at in this standard are going to be like integrate the function f of x comma y equals xy squared minus x over the region S is going to be a set of points, x comma y, satisfying -4 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 3. Dr. Gerstel, that's not the numbers in the packet. I'm changing the numbers in the packet on the fly. It's to give us nicer answers. So in Calc 3, these are going to be the sorts of questions we're looking at. instead of just saying, here's a function just in terms of x that we're integrating over an interval where x goes between two separate numbers like this, in Calc 3, we're going to be looking at multivariable functions. In this case, we have a function f going from R2 to R that we want to integrate over a two-dimensional region where both x and y can range between two different expressions. So let's take a look at what this is actually giving us. So if we graph this out, we'll have a y-axis here, z-axis here, an x-axis that's jumping out of the board at you. We'll go -4 in the x direction, +2 in the x direction, and then y is going to go from 0 to 3. Meaning the set we're going to be integrating over here is going to look something like this. This is just a set of points. A set of points whose z-coordinate is 0, and whose x goes from where x goes from -4 to 2, and y is going from 0 to 3. So here's what's going on. We're going to have some multivariable function, f of x, y, that's going to define a surface for us. So pretend like we have this sort of curved surface up throughout R3. So this is just going to be the set of points in R3 whose z-coordinate is equal to x times y squared minus x. And our goal is going to be ultimately, just like in Calc 1, where we were finding area between our function and the x-axis, here in Calc 3, we're also going to be looking for sort of how much space is being taken up in this region here. How much space is there between our surface, f of x, y, over this rectangular region here? So, in Calc 3, it's not going to be area under a curve we're going to be finding. Instead, we're looking at how much three-dimensional space is there between our surface and the xy plane over this region. And so if we were to ask that question, how much space is being taken up between our surface and the xy plane over this region, what are we actually finding? Not area, but what is the three-dimensional analog of area? We're finding volume. Exactly. So here, what we're really going to be doing is we're going to be finding volume underneath f of x, y, or let's say not under, but let's just say between f of x, y and the xy plane, meaning the plane where z is equal to 0, over the region S. Because technically, if we didn't fix ourselves to looking at over a specific region here, there'd be an infinite volume. Infinite volume going out in all possible directions. Just like in Calc 1, if we didn't take an interval that we were integrating over, we'd have an infinite amount of area between f of x and the x-axis. And so here, when we're finding the volume, we need to specify a region like this that's where x and y are kind of restricted in how far they can go in order to be able to get a finite volume. So that's what multivariable integral is going to be telling us. Any questions before we actually try to go and evaluate what is this integral going to come out to? So the idea in how you would evaluate an integral like this is pretty actually similar to Calc 1. We have a multivariable function, f of x, y. We're going to be integrating over our x boundaries, where x is going to go from -4 to 2, xy squared minus x. But the trick here for our multivariable function is after we've integrated with respect to x, we're then also going to have to integrate with respect to y as well. And in doing this, we're going to end up with two separate integrals to evaluate. Integral with respect to x, and also an integral with respect to the variable y. And doing this process is called doing a double integral. You just integrate with respect to x. After you're done doing that, we integrate with respect to y. Yeah, John?
Does the order matter?
Good question. We'll come back to that. We're going to come back to that in a few minutes. So let's see what happens when we try and integrate this. Let's see. Olivia, I pick on you first. If we were to try and take an antiderivative of xy squared minus x, but we're taking an antiderivative with respect to x, meaning we're treating y as a constant, what would be something that if we differentiated with respect to x would give us xy squared minus x?
1/2 x squared y squared
1/2 x squared y squared.
minus 1/2 x squared.
Like that? I like it. Yeah, that's absolutely right. This is going to be an expression that if we differentiated with respect to x would give us x times y squared minus x. In other words, if this is our f right here, del f del x would be this expression. And since we're integrating with respect to x, we need to plug in -4 and 2 according to the fundamental theorem of calculus. And all of that is still going to be inside an integral from 0 to 3, integrating with respect to y. So before we go on and integrate with respect to y, we need to finish the integration process with respect to x first. Meaning, we need to actually plug in our bounds 2 and -4 into one of our variables here. Holly, we're going to need to plug in 2 and -4 into either x or y. Which variable do you think we should plug those numbers into?
X.
Why x?
Because you just integrated with respect to x, so.
Yeah, I think that's pretty reasonable. We are integrating here with respect to x in our first step, and therefore it makes logical sense to plug in 4 and -2 for x and see what pops out. So if we do that, we'll get 1/2 times 2 squared times y squared minus 1/2 times 2 squared minus what we would get if we plugged in -4 for x. So 1/2 times -4 squared y squared minus 1/2 times -4 quantity squared. And if we simplify, let's see, 4 over 2 gives us a 2y squared, minus 4 over 2 is 2, minus the expression we would get if we took -4 squared is 16 over 2 is 8, so 8y squared, 16 minus 8. Which, once we actually plug those numbers in, which when we combine those two terms is going to give us an integral from 0 to 3 of -6y squared minus 2 plus 8 becomes a plus 6. So what we've done is we've done a Calc 1 integrate with respect to x so far. What the trick is that y has been treated as a constant. That's just kind of been brought along for the ride. Integrated with respect to x, we took an antiderivative, we plugged in our bounds for x and subtracted, and now we're just left with an expression in terms of the variable y. What do you think should be our next step? Because I'd like to be able to say, oh, the volume is this number, but our expression does not come out to a number just yet. What logically should we do with this? Gary?
Integrate with respect to y.
Let's integrate with respect to y this time. Jack, can you give me an antiderivative of negative 6y squared plus 6 with respect to y?
Negative 1/3, y to the third.
Negative. I'm going to say negative 6/3 y to the third.
Yeah.
So in other words, negative 2y cubed.
Plus 6y.
I like it. Something that now, if we differentiate with respect to y, we would get this expression. And now we can plug in our boundaries for y, since we integrated with respect to y, and let's see what that comes out to. It's going to be negative 2 times 3 cubed plus 6 times 3 minus negative 2 times 0 cubed plus 6 times 0. Which, oh, that's just 0. So negative 2 times 27 is negative 54. That's going to be plus 18. There's our answer. When we find the volume between f of xy and the xy plane over this rectangular region, we found that we got a volume of negative 36. Where to find that? We just started by integrating with respect to x. We took an antiderivative with respect to x, plugged in our x bounds, and after we did that, we took another antiderivative, this time with respect to y, and then plugged in our boundaries for y. Madeline, we got a negative number here for volume. What do you think that means about our curve and its relationship to the xy plane?
There's more negative space than positive.
Ooh, what do you mean by negative space?
It's like on the negative part of the axis.
Ah, so say underneath the xy plane?
Yeah.
Yeah. So the fact that this is negative tells us that this is not actually a very good picture of what's going on. There's actually more the surface is actually more underneath the xy plane than it is above the xy plane. So just like in Calc 1, where area under the curve, where area between the curve and the x-axis that was under the x-axis counted as negative area, here, volume that's underneath the xy plane, meaning if our surface dips below the xy plane to negative z values, that's going to be counted as negative volume. So there's more volume here under the xy plane than above. Any questions or comments about the process we just did with our double integral before I answer John's question from a few minutes ago? So John, you asked the question earlier of we integrated with respect to x and then with respect to y. What was your question again?
Can we just do that the other two with respect to y first?
Yeah. Could we have integrated with respect to y first and then with respect to x? Let's find out. So we got negative 36 if we integrated with respect to x and then with respect to y. Let's see what happens if we do it the other way around. Or now, I'm going to integrate with respect to y. Well, I shouldn't have erased the function first. Where, when I'm doing it with respect to y, I'm going to have the inside integral be from 0 to 3 xy squared minus x dy. And then we'll have the integral with respect to x be on the outside. So when we write out a double integral like this without the parentheses, it's usually understood that you do the inside integral first, meaning this is an integral with respect to y, and then the outside integral, and the dx term kind of on the outside here, is going to tell us here we're going to be integrating with respect to the variable x. So we're going to reverse the order of integration this time. And John, since you asked the question, I'll let you make the guess. Do you think we're going to get the same answer or a different answer than we did when we integrated with respect to x first?
I guess we're going to get the same answer, but I have no reason behind that. So
It's just sort of a wild guess? Yeah. Actually, you know what? Let's do a quick vote. Who thinks thumbs up for we're going to get the same answer, thumbs down for we're going to get a different answer? Seen a lot of thumbs up or indecision here. Let's find out. Let's see. Benu, can you give me an antiderivative of xy squared minus x, taken with respect to y this time?
X over 3, y to the y cubed minus x.
Not just minus x.
xy.
Minus xy. Taken from y equals 0 to y equals 3. Yeah. So now, we're going to start off by treating y as our variable and x as our constant. When we integrate with respect to y, which will give us this expression. And now we can plug in our y bounds, y equals 3, y equals 0. Which if we do that, is going to give us, actually, let's stop and ask this question first. Katie, when we plug in 0 and 3, are we going to be plugging them in for x or y here?
This is for y.
Because we just integrated with respect to y?
Right.
I like it. Yeah, these are values of y. So since we're integrating with respect to y, we're going to plug these in for y rather than x. So we'll get 1/3 x times 3 cubed minus x times 3 minus 1/3 x times 0 cubed minus x times 0. Integrate with respect to x. Which, when we evaluate that out, we'll get 27 divided by 3 is 9x minus 3x. And then that's just minus 0, so this all goes away. And we end up with an integral from -4 to 2 of 6x dx. So here again, we just plugged in our bounds on y, and x is just a constant term for now that's coming along for the ride. Hi x. Can you give me an antiderivative of 6x taken with respect to x? Okay, 3x squared, evaluated from x equals -4 to x equals 2. We plug that in and evaluate, we'll get 3 times 2 squared minus 3 times -4 squared, which 4 times 3 is 12, 16 times 3 is 48. Neato mosquito. Turns out, John, you were right. integrating with respect to y first and then with respect to x gave us the same answer as if we had integrated with respect to x and then with respect to y.
And then follow up, are there going to be differences in difficulty levels sometimes?
I don't know.
You know,
Sure.
I mean, not
Like,
really-
personally, I would say this
not
is-
on this one, but
Well, actually, I would say this doing y then x ended up being a little bit easier. Are there going to be some times where it's much more difficult to do it one way than the other way? Yes. And we're going to talk about those on Wednesday's class. So, good question though. So, turns out if we integrate with respect to x and then y, we get the same thing as if we integrated with respect to y and then x. At least in this example. See what happens if we look at a different example. So I'm going to flip forward actually a couple pages ahead in the packet. There's a big scary theorem called Houdini's theorem, but we're going to come back to it. And this time, I want to see what happens if we integrate a different function over a different region. So now, I'm going to be 2 pages ahead in the packet, and we're going to integrate the function f of x comma y equals x times y over the region D is going to be the set of points x comma y, where x is going to go from 0 to 3, and y is going to be between 0 and 2 minus 2/3 x. This one's going to be a little bit sneakier this time because y is not going between 2 different constants like in our first example. Instead here, x goes between 2 constants, but y goes between 0 and some expression in terms of x. So what's going to be the set that we're actually integrating over here? Well, x and y are both positive, so I don't need huge negative axes here. X is going to go from 0 up to 3. Y is going to go from 0 up to 2 minus 2/3 x. So if we look at the line y equals 2 minus 2/3 x, it's going to look like this. What's our region going to look like that we're integrating over? If x has to be between 0 and 3, y has to be between 0 and this line here, 2 minus 2/3 x. Yeah, we're getting this triangle right here. It's going to be the region that we're integrating. Let's see, if x equals 0, y is going to be 2, so this will be a y equals 2. Let's see what happens when we try integrating over this region. It's going to be a very similar process. We're going to do a double integral. This time, it's going to be just a smidgen more complicated. Who can I really pick on? Jackson. You want to integrate with respect to x first, and then with respect to y, or with respect to y first, and then with respect to x?
I would think y first, because when you evaluate it, you have x's in the equation, and then you'll be able to respect that.
Nice, I like the way you're thinking. Yeah, that was actually a trick question. I was going to do with respect to y first, no matter what you said. But I'm glad that you picked the way I wanted to go with it. So let's integrate this. We're going to integrate where x goes from 0 to 3. Y is going to go from 0 to 2 minus 2/3 x. And the function we're integrating is x times y. So first we'll integrate with respect to y, and then we'll integrate with respect to x. Just to see what happens. So if we do that, we'll get integral of xy. Lori, can you give me your favorite antiderivative of xy taken with respect to y?
1/2 x y squared.
1/2 xy squared? Sounds good to me. Evaluate it from y equals 0 to y equals 2 minus 2/3 x. And now, we need to plug in our two bounds for y into anywhere we see a y. So here, we're going to plug in 2 minus 2/3 x into the variable y, which will give us 1/2 x times 2 minus 2/3 x quantity squared, and then minus 1/2 x times 0 squared. Same process as before, except this time we have an x expression that we're plugging in for y rather than just a constant. And if we evaluate this out, I'm just going to go ahead and skip right to where I've already multiplied this out. This is going to be the integral of 2x minus 4/3 x squared plus 2/9 x cubed. And you would have to FOIL that out and multiply by 1/2 x to get to here. We integrate that with respect to x. Emily, what's that? How can we take an antiderivative of this with respect to x?
Well, it would be 2/3 x cubed.
I think you jumped up 2 powers instead of just 1.
Oh, it'd be x squared minus 0 over 9 x cubed plus 2 over 36 x.
Yep, I like it. I went ahead and just replaced 2 over 36 with 1 over 18 and just simplify the function a bit. So that's evaluated from 0 to 3, which is going to give us 3 squared minus 4/9 times 3 cubed plus 1/18 times 3 to the 4th minus 0 plus 0. We plug in 0 into any of these terms, just going to give us 0. Which will give us 9. 27 divided by 9 is 3 times 4 is 12. 81 over 18 is the same as 9 over 2. Negative 3 is equal to negative 6 halves plus 9 halves. Looks like we're going to get an answer in the end of positive 3 halves. Meaning it looks like there's going to be more positive volume, meaning the surface is more above the xy axis over this triangle than it is beneath it. More positive volume than there is negative volume. All right, John, we integrate the other way around. We're going to end up with the same thing. I'm not meaning to make you integrate this, do a double integral in your head on the spot.
Seems like a setup, so no.
John thinks this is a setup. I'm trying to trick him. Let's see if he's right. So now we're going to integrate 0 to 2 minus 2/3 x, 0 to 3 xy, taken with respect to x, taken with respect to y. See what happens. Integrate xy with respect to x will give us 1/2 x squared y. Wait, we're going to plug in 0 and 3 here for x or for y?
We are plugging it in for x.
We just integrated with respect to x. I agree. So that'll give us 1/2 times 3 squared y minus 1/2 times 0 squared y, which, hello Dr. Patel, or Mr. Patel, which means when we simplify, we're just going to have 9/2 y if we take an antiderivative now with respect to y, we'll get 9/4 y squared, evaluated from 2 minus 2/3 x to 0, or 0 to 2 minus 2/3 x, is going to give us, as our final answer, 9/4 times 2 minus 2/3 x quantity squared and minus 0. Is that the same answer we got before? If I were to multiply all of this out, is that going to simplify to just 3/2? Yeah?
It's still have a variable in the function and no way to move it.
Yeah, this has x's in it. This is like a polynomial in terms of x. Before, we got a 3/2. Well done, John, not falling for my trap. You were correct. It was a 7. Dad Zeus. It didn't give us the same thing this time. As Brianna pointed out, if we have the integral with this 2 minus 2/3 x is our second integral, it's our outside integral, then our final answer is going to have x's in it. Because we're not integrating this anymore. If we were to integrate this from x equals something to x equals something else, we could get this down to a number. But that was our second integral. There's no more integrals to take. And so, whenever you're integrating something like this, you're not going to be able to just swap the order all willy-nilly necessarily. When x and y go between two constant values, like they did in the first example, you can swap the order of integration pretty easily. But you can't do it in this example because when the 2 minus 2/3 x integral was on the inside, then when we plug that in for y and integrated with respect to x, we could get to a number as our final answer. But when this integral was on the outside, well, our final answer is just going to have x's in it, and since we're not integrating anymore, there's no way to get rid of them. Jacob.
Oh boy.
We got 2 different answers.
Which one's right?
Which one was the correct answer?
One that gave us a number.
Yeah. Turns out this one gave us a number, and this was the correct answer. The volume we're finding volume. Volume should be a number. It shouldn't be, oh, I'm not going to go to the supermarket and say, hey, I need to purchase an aquarium. Oh, how much water do you want your aquarium to hold? Oh, I want it to hold 9/4 times 2 minus 2/3 x quantity squared. What? 3/2 is correct. This is actually all. Whenever you do a double integral like this, you want to be able to come out with a number in the end. Because volume is going to correspond to a numerical value, not to a polynomial. Unless you had something like set this equal to 0 and solve for x, something like that, which we do not have in this case. Jackson?
I guess the next trick question would be, what if you have functions of x and y and both of the intervals?
Then you would be up shit creek without a paddle. That would actually be a region you couldn't integrate very easily over. You'd have to do some trickery, which we're going to be talking about on next week. But before I let you go for the day, there is actually a way that we can integrate this with respect to x and then with respect to y and get a correct answer. But it's a little bit trickier than just swapping the 2 integrals like this. What we can do is we can rewrite this region so that instead of having x go between 2 constants and y go between 0 and an expression of x, I claim we can rewrite this region so that y is going to go between two constants, and x is going to go between 0 and an expression in terms of y. And the way we would do that, take this equation, y equals 2 minus 2/3 x. And Brianna?
Right, in terms of x.
Solve for x. So if we do that, we'll get negative 2/3 x equals y minus 2. So that x should be negative 3/2 times y minus 2, which is the same as negative 3/2 y plus 3. And it turns out another way to write this same set of points is to let y go from 0 up to 2, and to let x go from 0 to negative 3/2 y plus 3. Because x equals negative 3/2 y plus 3 is going to be an equation for the exact same line, just written in a different way. 0 less than or equal to x less than or equal to negative 3/2 y plus 3. And now, if we rewrite our integral, like this, where our inside integral is going to be in terms of x, where x goes from 0 to negative 3/2 y plus 3, and our outside integral is going to go from 0 to 2 dx. I claim now that we've rewritten our region in a way where x is going between two expressions in terms of y, and y goes between two constants. I think we should be able to integrate this and come out to, hopefully, a number for our answer. So, to integrate with respect to x, we'll get 1/2 x squared y, evaluated from 0 to negative 3/2 y plus 3. I'm going to plug in negative 3/2 y plus 3 and 0 into x this time, because we integrated with respect to x first. So we'll get 1/2 times negative 3/2 y plus 3 quantity squared y minus 0. When we multiply that out, in the interest of time, I'm just going to tell you what that multiplies out to. It comes out to 9/2 y minus 9/2 y squared plus 9/8 y cubed. Now, when we integrate that, we'll get 9/4 y squared minus 9/6, so minus 3/2 y cubed, plus 9/32 y to the 4th. And this is going to be from y equals 0 to y equals 2. 2 squared is 4, divided by 4 is 1, times 9 is 9. 2 cubed is 8, over 2 is 4, times 3 is 12. 16 over 32 is a half, so this comes out to plus 9/2. And then technically minus 0 plus 0. Negative 3 plus 9/2 is the same as negative 6/2 plus 9/2. Oh snap. We got 3/2 again. So what's the moral of the story? The moral of the story is, can you swap the order of integration? The answer is generally going to be yes, but it's a little bit more complicated than just taking an integral and swapping the order of the two, because you always need to have the integral on the integral on the outside always has to go between two constants. And the theorem that tells us this is the big scary theorem I skipped on the 3rd page of the packet, called Fubini's theorem. Where in the packet it's written out in great detail, but intuitively, what I want you to think of when you think of Houdini's theorem is going to be you can swap the order of integration but you may need to rewrite, but the outside integral always has to be between two constants. Is essentially what Houdini's theorem says. And if you have something where the inside integral goes between two different expressions of like x, like the second example did, if you want to swap the order of integration, you're going to need to rewrite your domain so you can still write it so that the inside integral is the one that has variables in it, but the outside integral has to go from one constant to another constant. All right, that's going to do it for today. All right, actually, I had more time left than I thought. Hey, that's going to do it for today. So on Monday, we'll have the exam, and on Wednesday, John, I'll answer one of your questions I didn't get to earlier, which is there ever a time when it's when it's significantly easier or more difficult to integrate with respect to one variable than with respect to with one variable first than the other one first? Answer, spoiler alert, is going to be yes.